All right, we're going to take a look at half-life. First of all, let's define what is meant by half-life. So half-life is the amount of time required for a substance. Let's see. Let's take that out just a little bit so you can see. Here we go. The amount of time required for a substance to decay to half its original amount. The amount of time required for a substance to decay to half its original amount. And this is why we call it half-life. Every substance has its own half-life number. Some things decay quickly, and some things require lots and lots of years. There's a formula that we can use for half-life, and I'm going to write it up here at the top of your paper. Okay, and it looks like this. All right, so it's A equals A sub 0 times 1/2 to the power of, and your exponent is a fraction, t divided by h. So A, what you're finding is the final amount. The final amount of your substance. And then the A with a little subscript of a 0, this is your original amount. T is the amount of time that has passed. And H is the half-life of this particular substance. And half-life is often written with a hyphen between it. All right, so this is the formula that you can sometimes use, and these are the what the variables represent. So the formula is most useful whenever what you're trying to find is this final amount. That's when it's most useful. If that's all you want to know, then you can plug your numbers into this formula and figure it out. Let's talk a little bit about half-life. In problem number 2, it says if you have 100 grams of a radioactive isotope with a half-life of 10 years, and then we can finish that question with A, B, or C. So if you have 100 grams of a radioactive isotope with a half-life of 10 years, A, how much of the isotope will you have left after 10 years? Well, again, let's refer back to the definition of half-life. It's the amount of time it takes for the substance to decay to half its original amount. So we could just use logic here. I see that I'm starting with 100 grams of this particular substance. It has a half-life of 10 years. So that means after 10 years, the amount that we started with will be half. So I could simply say 50 grams, which I could abbreviate 50G. So I could just logically figure that out. But if you didn't, let's say you didn't realize that and you wanted to use the formula, it's asking for how much will you have left, which is a perfect opportunity to use the formula. The original amount goes here, that's 100 times 1/2. This is always 1/2 in these formulas. The time is 10 years, divided by the half-life is also 10 years. And if you did all that, you would also get 50. How much of the isotope will you have left after 20 years? Well, after 20 years, that's another 10 years, it's going to half again. And half of 50 grams is 25 grams. So you could just logically figure this out. But again, you could use the formula which says start with your original amount times 1/2. But this time T is 20 years. But the half-life is still 10 because we're still talking about the same original substance, this radioactive isotope, and its half-life is still 10 years. And if you did this math in your calculator, you would get 25. Question C says, how many half-lives will occur in 40 years? Well, a half-life is every 10 years. And so 40 years is 4 sets of 10 years. So there will be 4 half-lives in 40 years for this particular substance. Remember, every substance has its own half-life. All right, let's take a look at another one. Let's take a look at number 3. It says the half-life of plutonium-239 is 24,300 years. If a nuclear bomb released 8 kilograms of this isotope, how many years would pass before the amount is reduced to 1 kilogram? So this time the question is about how many years? Yes, sir. You can come look, sweetheart. So the question is how many years, not what's the final amount. So if you go back to this formula, I'm looking for T, and that would be a little difficult to find. So what we might want to do in this case, and what you can do in a lot of cases, is create a table. And I'm going to use a separate sheet of paper to help me with this. So let's write down the important information here. So we have this substance, plutonium-239. Its half-life is 24,300 years. This is a very stable substance. It decays very slowly. Now, the nuclear bomb originally released, so the original amount, A sub 0, is 8 kilograms. And we want to know how many years, so how much time it takes before the amount is reduced to 1 kilogram. All right, let's just concentrate on this for just a moment. Now let's suppose that you entered this into the formula. A equals A sub 0 times 1/2 to the T divided by H. So your final amount is 1. Your original amount is 8. 1/2. T is what you don't know, and half-life is 24,300. You can see that you're solving for T. That would kind of be difficult using this formula. But I have got a very simple solution when a problem seems too difficult. Make a table, okay? Make a table with the time and the amount of your substance. This works many, many times to help you with your problem. Always start with times 0. The original amount is at times 0, and we had 8 kilograms. Now, the half-life is 24,300 years. So the next time we're going to be worried about is 24,300 years. This is going to half to 4 kilograms. We want to know, when is it going to be 1 kilogram? So let's keep halving. Half of 4 is 2, but that's going to take another 24,300 years. So if I add another 24,300 years, this is going to be 48,600 years. And then I'm going to half this again. Half of 2 is 1 kilogram. But that's going to take another half-life, another 24,300 years. So if I add another 24,300 years, I'm going to end up at 72,900 years. And so that gives me my answer. After 72,900 years, 8 kilograms of this substance will decay to only 1 kilogram. Okay. So I'll go back here and answer number 3. So that was 72,900 years. Wow. So making a table can be very, very helpful in problems like this. Let's take a look at number 4. It says the half-life of radon-222 is 3.8 days. How much of a 100-gram sample is left after 15.2 days? So the first thing we're told is the half-life. Now this number 222 and in the previous problem 239, that's part of the name of the substance. So those numbers do not come into play into the formula. So for number 4, the half-life, which is represented by H, is 3.8 days. It only takes 3.8 days for the substance to half itself. How much of a 100-gram sample is left after 15.2 days? So the 100 grams must be the original amount. And then we want to know how much is left after 15.2 days, so that must be the time. This is a perfect problem to utilize the formula. Okay, so I'm going to show you how you can do that. Okay, so let me actually get another sheet of paper. All right, so here's what we have discussed so far for number 4. That the half-life is 3.8 days. That the original amount was 100 grams. And we want to know what happens after 15.2 days. If we substitute these into the formula, the amount is going to be the original amount, which is 100, times 1/2 to the power of time, 15.2, divided by half-life, 3.8. Now, if you'll excuse me for a moment, I'm going to head on over to my Desmos calculator, and I am going to type this in. And of course, you could type this into your Inspire calculator. 1/2 to the power of 15.2 divided by 3.8, and I get 6.25 grams. Now, I'd like to show you how you could do this with a table if you like. So remember, for a table, you're going to have time and amount. Always start at time 0. This is your original amount, which was 100 grams. The half-life is 3.8 days. So 3.8 days later, you're going to half this substance to 50 grams. If you add another 3.8 days, which would be a total of 7.6 days, you're going to half the substance again. Add another 3.8 days, and you'll half the substance again. Half of 25 is 12.5. Now I'm trying to get to this magic number here, 15.2. And if I add 3.8, guess what I get? 15.2. Okay. And so I half 12.5, and half of 12.5 is 6.25 grams. That's the same thing that I got in the formula. So I've just shown you two different ways that you could get to the answer. I think in this case, the formula is quicker, but I like the table because it really shows you what's happening. So let's go back. So number 4, we answered. After 15.2 days, we would be left with 6.25 grams of the substance radon 222. Let's try just one more together. Carbon-14 has a half-life of 5,730 years. If a sample contained 70 milligrams originally, how much is left after 17,190 years? This is another great problem for the formula if you like the formula. So the half-life, that's our H value, is 5,730. It contained 70 milligrams originally, and we want to know how much is left after 17,190 years. Okay, let's go to our paper. And let's answer this. So what did we decide? We decided that the half-life for this particular substance, carbon-14, is 5,730 years. We know that the sample originally contained 70 milligrams. And we want to know how much is left after a time of 17,190 years. Okay, if you plug these into the formula, you can find your final amount. Your original amount times 1/2 to the power of time divided by height, which is 5730. All right, so once again, let's take a moment to type this in our calculator. All right, so 70 times 1/2 to the power of 117,190 divided by 5730. And I get 8.75. And we're measuring in milligrams. But again, just for kicks, let's try this in the table and see what happens. So let's see, we have time and we have amount. Again, always start at time 0. The original amount was 70 milligrams. And every 5,730 years, we're going to cut this amount in half. So let's go ahead and go to the first half-life, 5,730. And this is going to be 35 milligrams because half of 70 is 35. Now let's go a second half-life. So add another 5,730. Now you're at 11,460 years, and you're going to half this again, which would be 17.5 milligrams. Let's add another 5,730. What do you know? We're at 17,190 years. So we're going to half 17.5 again. And let's see, what's that going to be? 8.75. What do you know? Exactly the same answer we got with the formula. So let's go back and write our answer down. So for number 5, we're going to have 8.75 milligrams of this carbon 14 after 17,190 years. So use the formula or use the table. The formula works best when you're looking for the final amount, but the table is really nice to use most of the time. I hope this helps. Thanks, guys.